Hello, everyone. Thank you for coming to another seminar and today for being so punctual. Usually we start at 12:05 and today is even earlier. Today we have Laura Gómez. She's a postdoc at the Operational Marine Technology and Operational Oceanography Group, and she will be talking about her research on some physics topics. So thank you very much.
Thank you, Nicholas. Well, I tried to put a friendly title, but I see that physics is the main word. Well, I think I need to specify I'm Laura Gómez Navarro because we're Laura Gómez, so be careful. And I will talk about my previous work. And I did a postdoc before coming back here to Midea in the Utrecht University in the Netherlands. And we touched several topics, but so I put it all together in this, how can ocean physics help with marine pollution? So, well, I'll try to bring you with me this journey. But just to mention a bit, right now here at Imedea, I'm working on the FastShot project. So with this satellite here that measures the sea level, and we're working on some data and campaigns that took place here north of Mallorca. But yeah, this is ongoing work. And going back to what I did previously, I was involved in two projects, one from the European Space Agency, that what they do is from time to time, they put together new products of ocean currents, and then which they try to do it like practical cases. And our practical cases were like applying it to oil spills and sargassum. And then in the team there in Utrecht, there was a big project on tracking floating plastic. And I looked a bit on some of the fine scale processes that can affect the tracking of plastics in the ocean. So to give a bit the motivation, so yeah, understanding the surface dispersion of and accumulation is important to trace different materials from plastic to oil spills and certain algae too. And when we do trajectories to know where these different contaminants will go, we use usually velocity data from different models. And you hear me okay or no? Okay, I'll try to speak loud. And these different data products of the currents, they have different characteristics, but we don't always know how good they are. And sometimes, okay, if we want to look something at the Mediterranean scale, for example, maybe we don't care about the small K processes, which I will refer to as high frequency motions, and I will try to show you how these sometimes small scales in the ocean can affect very larger trajectories and bigger problems like the different pollutants we can see here. So yes, we will try to see how this ocean physics, these small scale motions can impact the trajectories of different pollutants, and then this contribute to maybe doing better policies in managing all this pollution. So only a bit of theory, no equations, I promise. When we talk sometimes about the different ocean dynamics we divide them in the different temporal and spatial scales, no? And there's some that are very well known to all of us, no? That are the surface waves in the ocean that are around here. And then with the current data and technologies we have, we define like this scale around 100 kilometers, that here is more or less the processes that we would be able to resolve and reconstruct properly, and below is processes that maybe not so well or that we're starting to improve, like for example with the SWOT data. And for example, yeah, above this we have processes like the climate change, and then below we have other maybe less well-known processes from which I will talk today that are internal waves. So we saw before that we have the surface waves in the ocean, but also in between ocean layers we also have internal waves, and these have a lot of impacts. Like they can also have an impact on transport and on breaking the mixed layer, and they are quite an interesting process that we're starting to observe now. And for example, you can observe these waves here. This is the Strait of Gibraltar, and you can observe sometimes this internal wave signal at the surface when the water comes in. And then a bit more in this intersection of what we can observe and what we cannot observe. We have eddies and fronts. So eddies are these like structures we have here, And then we have different fronts and filaments that also are very important as it's where like different pollutants can accumulate. And aside from pollution, these fan scale dynamics below the reference line I showed you are very important because it doesn't only define our surface transport, but also exchanges in the vertical. And this also has very important geochemical applications. But for today, I will only focus on the surface ocean. So yes, I was saying we have all these different ocean dynamics. And for today, to see how the ocean physics affects pollution, I will mainly focus on two of these motions, the internal waves I mentioned, and also inertial oscillations that I will show you now more in detail what these are. So moving to this first part, we focus on different case studies, no? Because okay, we can try to understand the dynamics, but then we need to see if it really works. And we focus on sargassum and oil spills and in different use cases that happen. So one is when we are it's not very often, but sometimes we manage to observe these sargassum mats on the surface ocean and track them. And the other unfortunate oil spills that even if it's a very sad case when it happens, we can try to retrieve some information to, if it happens again, be able to manage it properly. So first focusing on the sargassum. For those of you who don't know, it's a brown macroalgae, and it's usually found in the tropics in the Sargasso Sea, the only sea without a coastline. And why it's important to monitor it, like of course this sargasso is not a pollutant per se, but in recent years it has become a very big problem as these huge quantities of the sargasso are arriving at the Caribbean islands. And we don't really know why yet. And it has a very big impact on local ecosystems and tourism. You see how tourists get here about a bit of Posidonia, so imagine here with all this sargasso. And then what we do is, like you can see here, this is a trajectory of a drifter, of a drifting buoy. And the continuous line is the drifter trajectory. And you can see that there are these oscillations like this, and this is what we call the inertial oscillations. And these usually are not included in the current products we use. And in this project, a colleague, Clement, he did a procedure to start to include these inertial oscillations, and you can see it in the trajectory above the dashed line. Of course, there's not as many, but we start to include this dynamic. And what we did, working with the French Operational Center, Meteo France, we compared the current system they have to track this sargasso with our own simulator and the new current products, and also adding other effects. No, we'll see here that when we look at pollutants, the main thing is not only ocean currents, but also the impact of the winds and the stock drift, which is the drift due to the waves. Okay, so unfortunately for the Sargasso satellite images, we don't have a lot of data. So with what we managed to get, we did what we could. And during May, close to the island of Barbados, there are some colleagues from Meteo France, they managed to identify these big Sargasso mats floating on the sea and track them only during 24 hours. Due to the nature of this satellite data, it's very easy to lose track of it because this data is affected by clouds, and sometimes you may not know if it's the same mat anymore. But well, we had this small data to do some tests just to see how important this is to have these different considerations in the ocean dynamics. And this is what we did. Like the top panel is the operational case, and the bottom panel is what we did. So it's a lot of information here, but the thing to notice that also when you do like Lagrangian trajectories and do these simulations, there's quite some simulators you can use, but at the end of the day, the important part is the underlying data you use, right? And how you configure it. You can see here in our configuration, to take into account this uncertainty in the dispersion, we released an array of particles around the initial point. But the way they do it in the operational center is that they add a diffusion parameter that creates this dispersion of trajectories. We prefer to be a bit more conservative to not put a diffusion value that we don't really know if it's correct or not. And well, some small conclusions we could take of this is that even if it's very little data, we could see that it was important to not only have this improved, we call it the walk product, with inertial oscillations, but of course that it's necessary to combine it with correct winds and wave data. And yeah, that of course that small differences can happen, that maybe if we do the average distance, it should be a bit more south than north, but it was already some motivating results to see that we were improving the data in the correct direction. That sometimes, well, with this few data, it's already something to look forward to. And then with the oil spills, at least in my case, we don't hear luckily that often anymore about any oil spill situation, but it still happens unfortunately quite often. For example, in 2021, I don't know if some of you heard of it, but there was a big oil spill east of the island of Corsica. You can see here the slick signal. So it's still quite something that unfortunately has to be tackled often. Here we collaborated with an NGO that works on managing when there's an oil spill and seeing that the impact is as little as possible. And for this, they had some data in these islands in Japan. So you have Shanghai, and this is off the coast of China. You have this just south of the Japanese archipelago. And what happened is there was an incident in January 2018 where a ship sank in this red dot in this location because of the collision of an oil tanker with a cargo ship. How did that happen? No, who knows? And especially, well, quite of the islands were affected, but especially these islands of Takarajima and Amami. And what we did is we released some particles here. We used this new ocean currents product, and we added also the effect of the winds and of the waves. And of course, it's also important here, it was nice that we could have a lot of details of the pollution event itself, because they could tell us that the sinking ship was losing oil during 10 days. So this also adds quite some realism to the simulation, as you can be releasing here particles, which don't move. And we can see the trajectory and how these particles, then we can evaluate how these virtual particles that we released affected the different islands here. And because it was quite particular that it was only this island of Takarajima and Amami, and not so much like some of the very close islands were not affected at all. It looks like the oil spill just crosses, because it's true that we're limited also by the resolution of the data. So well, with these simulations, we then evaluate with the different products how the oil spill was affected. So this is just the overview of the full trajectory using the old data sets that were available for these currents, the operational setup that they were using in the NGO, and our new data sets with also the winds and waves. And when we compared the impact on the different coastlines at the island of Takarajima and Amami, so the lowest, the better, we can see that with the product that we developed, together with also the wind data and the wave product developed in the project, we obtained the best accordance. So a bit to wrap up this first part, we can see some improvement already when we include, like you saw, it was like these very small oscillations, but when you're looking at trajectories of pollutants, any small change can already change a lot where the pollution ends up ending. And also how it's important to combine it with the different dynamics, to not just focus on the currents, but on the correct implementation of the wind and waves effects. But as you saw, we were very limited by the data available, that even if it's very big pollution problems, we still have very little data. And it's true that we also had problems to have some of the oil spill data because it was private data, not public. So anyways, a bit of negotiation there. And of course, even if we're going towards these smaller scales, we can see that there are still some features which are missing. We can see one of the cases, there was a very small eddy, just where we were looking at the dispersion. And so of course, only that change in this feature changed everything, and it was a disaster. So as I was saying, the main challenges we found here was the availability of data for validation, and then the representation of these small structures. And then I didn't show it here, but we also have a problem with the data nearshore. Now we're starting to have better data close to the coastline, but before, like, people were like, okay, we need to know where it lands exactly, this pollution, but you cannot sometimes trust the data at less than 100 kilometers from the coast. So you need to find a bit of equilibrium between both. And of course, then all of the data is important, but at the end of the day, what is important is to have these simulations near real time. And this also makes it an even bigger challenge because you have to process and adapt all of the data, and in the meantime, the pollution keeps moving. Okay, if there's some questions in this first part, if not, I move on. Bueno, pues later. Yeah, the other part I wanted to talk about, sorry, yeah, it's a bit more. It's about the plastics. I call it the plastic part, but at the end of the day, we're just calling it's virtual particles. And we looked at the effect of tides now, focusing on the Azores region. And as I told you before, in this, we have this called the internal waves, and in the Azores region, there's a lot of these waves happening there. So we wanted to see the impact of this, if these internal waves could really have an impact on the transport of plastics or any other pollutant in the area. And this came a bit from the motivation that in our field in satellite data, we use a lot of this spectrum that tell us the energy at different scales. And we can see that when you use model data with or without tides, there's a lot of difference in the energetics. So one would say, okay, this should then affect how things move in the surface if you have more or less energy. And to look at that, we use some model data that has no and has tidal forcing. And here you can see, well, here you see the vorticity fields, and well, this animation is not working, but well, the thing to notice here is that you can, when you just see at the animation of this trace of this vorticity, you can see that there is something happening, that it looks like there's a kind of vibration in the surface, no? So we wondered how this could then impact all these trajectories, because there's a lot of studies being done to say very specific things, for example, about plastic trajectories, but many of these studies don't include tidal forcing. So we did some simulations. Here you can see what I was mentioning before, that you have like, it looks like this vibration at the surface. So we use these models to do some simulations around on this area of the Azores Island, and we then assess the different accumulation patterns. And one first result that was quite interesting is that we compared the distances of, if you look at the distance traveled in a month of a particle, like the cumulative, so all along the trajectory, or the total one, we found opposite results. So when you looked at the cumulative distance, these distances were smaller with no tides than with tides. But when you looked at the total distance, this was bigger when there was no tides than tides. So again, going back to this vibration we see, if there's a particle moving, if it's like vibrating along the way, at the end it doesn't reach so far, but it looks like it's done more of a path on its way to its final destination. And then also we looked at the pattern. This is like a 2D histogram of the accumulation of particles after 1 month. And in the top you have without tides, and in the bottom with tides, and in the northern hemisphere winter. And you can see here that without tides there's a big accumulation, but when we include tides, not so much. And our hypothesis was that what is happening is that these, for example, eddy structures that can accumulate plastic, when you add this high frequency motion, it destroys it, and there's not so much accumulation happening anymore. And then in summer, we found the opposite, that there was more accumulation in summer with tides than without, but because there's these other structures, that internal waves that are more frequent. And the last thing we looked at, and also in collaboration with Ismael and Veronica, was looking at these plots of the Lyapunov exponents, that what they are is just like you can interpret them as barriers of transport. So it could be a bit like, for example, the skeleton of these eddies I was talking about. And here you can see very nicely, like in the top panel in January, in the left, when you don't have tides, you can see these nice circular structures, but when we include tides, these structures are like broken. So it supports a bit the idea that something is happening there that is changing on all our accumulation patterns. And then in spring, what we have is like when we include tides, we have all this input of energy, and it's much more turbulent. So well, this is to show you a bit that we saw that the main conclusion is that the importance of tidal forcing when you look at this, want to do this Lagrangian simulation, especially when they're applied to look at trajectories of any pollutant like plastics. And of course, here we focused in a particular region where we knew this signal was high, but well, it would be interesting to see in other areas, for example, like the Mediterranean Sea, that it's not considered to be important if still this tidal signal is breaking the structures here and affecting everything. And well, it is, I try to convince you that I hope that it's important to look at this high frequency motion. And when we try to understand all this, maybe you think like weird ocean physics dynamics, it's at the end of the day important to, when we want to apply it for ocean trajectories, to understand marine pollution. And that's it. Thank you.
Thank you, Laura. Any questions?
I'm wondering this. I'm thinking about the Mediterranean versus the Atlantic, for example, they have very tides. And this mechanism that you are showing, how do you think it could affect? That's nice. The way that it works. I mean, thinking more in terms of biological dynamic.
I'm sorry, I got distracted to the automatic change. And you say more the impact of the tides also in biochemically.
Yeah, so this interaction between the small scale processes and the tides. And
yeah, I think it goes back to then more also a part of the steering of the different, like for example, nutrients in the surface. It's also these internal waves. They also contribute to the vertical transport. So it has been shown that in some cases they are quite important to, as I mentioned, to break this barrier of the mixed layer and do more, contribute to the mixing of vertically of the ocean. And then, yes, this more precisely if the signal is high, but then, yeah, I would think that as we keep including all these high frequency processes, even if in other areas, I have, yeah, the suspicion that it will start to break all these patterns that we have known till now, like the eddies that can accumulate different materials that also they can be geochemical. Yes.
You showed me, so in this graph where you showed the vortices without tidal force and with tidal forces, so with tides, they look completely different, right? The vortices. And could you verify this model with any observation?
This one or the
See this
one?
one?
Yeah.
Is there any gliders or observational data?
No, we have no data here. Like this study was first to know if their impact was there because we had seen it in another context, first to show you of the energy spectra.
Yeah.
And then, yeah, here we saw that there was the impact, but not really there. We tried to see, we had the campaign in the Northern Pacific, and we were like, okay, we can see that there's some signals of internal waves. Maybe we can release some instruments, but it's hard to detect, or maybe we were unlucky and we didn't observe any of those features at that time. You need to see the internal. No, well, also because this is the model date, so it doesn't really correspond with the satellite data. But also, I don't know if at this resolution, this is around 1 kilometer. So I'm not sure with the still perfect. Yeah.
What was the main of the guys in that area that when not
I don't know, but I think it's maybe around 5-6 meters, if I'm not saying. But I think I'm approximating from seeing it because we're looking at it. I looked at it always more in terms of energetic. So okay, it's a high energy signal, not so much about the sea level impact. Well, if there's no more questions, I'll leave this here of also the importance of open science for all this study that I think we usually think it's only publishing in an open access journal or sharing your code and data, but there's a lot of other actions that take part of that, from the Instagram account to the committee reward that we have now, to also doing some things in Spanish and not only English all the time, or Italian or whatever. And yes, to give you some ideas to hopefully motivate more things.